This is a brand new in-box Gakken FX computer. It was originally released in 1981 in Japan as the Gakken FX-Micom R-165. In the UK, the FX computer was distributed by Electroni-Kit, and we can see their address penciled onto the fragile label here as 388 St John Street, which is in London. As this is the original shipping box, we'll see some nice vintage 1980s stamps, and I've covered over the address of the original owner on the box here. Now, rather than manhandle the computer out of this box on camera, I've taken the liberty of removing it from the box, and it's sitting just underneath here. So this is the original retail packaging of the FX computer, and as you can see, it's an electronics and computer kit aimed at children. It was known as the R165 in Japan because it includes 100 computer programs plus 65 electronic circuits, R165. The programs are programmed in using this electronic block here, which contains the computer unit, and the electronic circuits are built with these translucent green blocks here. Now, the FX system was an extension of the previous EX system by the Gakken company, and I have a magazine here from Japan which details the evolution of that series of different educational kits. Now, if we flick through the magazine here, we can find the relevant page detailing that evolution, and we can see the various EX series kits, ranging from the EX15 all the way through to the Japanese exclusive EX181. The main unit in the series was the EX150, and these were released throughout the 1970s until they were eventually replaced by the FX series in the 1980s. Here we can see the FX Micom R-165, which was released in 1981 for 14,500 yen, and the FX Clock and Melody unit, which was released in 1981 as well, this time for 16,500 yen. Now, I do actually have an EX kit series electronics kit, and I can show you that here. So this is the EX150, which, as I say, is the main unit in the series. And if we look inside, we can see some co-branding by both Gakken, the original producer, and Electroni-Kit, who was the UK distributor. Now, if you excuse the squeaking here as I pick this up, you can see this particular FX computer was released in 1982. In fact, the date is 25th of October 1982, which is when this unit would have been produced. By 1983, there were some magazine articles reviewing the FX computer, and I have a few of those here as well. And so this is an article and review from Everyday Electronics in May 1983. They give a very balanced review of the kit, saying it's definitely educational, although they do mention that the manual can get slightly confusing in places, so that's something to look out for. By October 1983, the magazine Hobby Electronics had their own review. Here they were much more complimentary about the manual. In fact, they discuss and detail several of the illustrations from the manual here, although they are somewhat critical about the lack of integration between the electronics aspects and the computer aspects. In fact, they describe it as an odd couple. They're particularly critical of the lack of logic circuits. However, they do note that the kits have been given a Japanese design prize by the Japanese Ministry of Science and Technology, and they say that this may start some interesting trends, which we might see just a little bit later. Just the next month, however, in November 1983, there's this article and review from PCW magazine, or Personal Computer World magazine, and here they talk about predominantly the computer unit itself, and if we look through here, they provide some details of the instruction set used, pointing out that it's a little obscure. They talk about the memory, which they point out is quite limited, but they do show a memory map, and they also really focus in on the price of the unit. Now, by 1983, it was possible to buy a ZX81, which had come out 2 years earlier, plus a 16 kilobyte RAM pack expansion unit for just £45, and they point out that's £25 cheaper than the FX computer, which was retailing at that point at £69.95. If we convert that to today's money, that's a little over £240, including the shipping cost, which of course my particular unit would have incurred. Now, the previous article did mention this might set off some interesting trends, and actually it really did. So by 1985, Tandy had decided to repackage the FX computer as the Microcomputer Trainer under their Science Fair brand, and you can see one of those just here. This particular unit is based on the spring terminals common with the electronic circuit kits from Tandy and RadioShack in the Science Fair branding at the time, although unlike the FX computer, they'd shied away from the electronics aspect and they indeed only focus on the 100 computer programs in the 180-page manual. More recently still, Gakken themselves released a new MOOC, or magazine book, in 2009 about the GMC4. Now the GMC4 is a modern reproduction and simulation of the original FX computer using the same instruction set. In this magazine there is an interesting article, and if we just flip through to that here, all about the development of the original FX R-165, as you can see here. And this details its conception in 1980 all the way through to its release in 1981. Now I've gone ahead and scanned a copy of that article here, and I also have a translation detailing the development of this particular kit, and I'll provide links to that in the description if you find those of interest. However, without any further ado, let's look and see what you got in your FX computer for your $69.95 back in 1980. So underneath the very nice lid here, pristine quality, we can see the FX computer system, and it has some bubble wrap protecting the unit. We have this nice foldable cover here, which has some bubble wrap here, holding the blocks in place and protecting the unit, and that would have been original packaging material. You can see all of the green translucent electronic blocks, and there are some more here to create the various circuits, as well as the main computer unit here, a CDS light sensor unit, which could be replaced with the optional clock unit, which, if you did purchase, could be stored in this space here. This particular space here is provided so you can store the batteries when the device is not in use, and there's also a few leads here that you can use for connecting to external electronic circuits. The unit has a built-in amplifier and volume control as well. If we remove this packaging piece here, we can see the handle that allows you to pick up the unit that folds quite nicely, and we can remove the unit, excuse the squeaking, from the box. As you can see, the clear cover allows you to stand the unit up without fear of the blocks falling out. In the rest of the packaging, we have a note from Electroni-Kit detailing some errata for the unit and some corrections that need to be made to the manual. We have the parts list and warranty card, which is quite nice here, including a registration card as well. And on the back, we can see the various blocks you can buy as additional parts, including a replacement computer for just £17, the sound block and the clock unit, both from the clock and melody kit. So you could actually convert your FX computer kit to a clock and melody kit if you like, including buying the manual as well for just £3. Getting down to the computer parts, we have the manual here as well. This includes a quick reference card for the FX computer, and this is a really nice reference card. It helps you program the computer, and on the back side we have some detail about the conditional flags that are used for conditional jumps in the program, allowing you to write more complicated programs. As I've mentioned, the kit is made up of two different parts, the electronic part and the computer part, and the electronic part is detailed in the 65 Electronic Projects Manual, and this has an errata sheet already glued in the front, but there's some really nice details here, illustrations of the unit, how some basic electronic circuit components work, and then we go through to some nice illustrations of various circuits you can build. They start off quite simple and slowly build up to more complicated circuits. The second manual contains the 100 computer programs that you can program into the unit. Of course, you can program in as many as you like, but there's 100 provided in this manual. And again, very nicely designed, some illustrations of the unit, how to control it, detail about the built-in music and sound options, and some built-in games, and then moving on to writing your own programs, detailing all of those instructions and showing contextually appropriate programs for them, illustrating their use. As you can see, the programs are all provided with the instruction code that you need to enter into the machine, a flowchart explaining the operation, and finally some text detailing how to operate that particular program. You'll see various call-out boxes, such as this one here, detailing exactly how a particular instruction works in the machine. And these are referenced from the quick reference card. So at the end of the manual, there are some details on how to operate the electronic component with the machine, and so using the input commands to control the computer from some electronic circuits. Now, as you can see, these aren't even numbered as part of the build of the 100 programs, so I think that is a fair comment of one of the articles that these two parts aren't particularly well integrated, and there are only actually two particular circuits and programs that use that functionality. At the very end, as you might have just seen, there is a program title or program instruction sheet that you can fill in with your own programs, and we'll look at some of those in a moment. So again, this is the unit here. If you just give me a moment to tidy this all away, we will have a look more closely at the unit and look at some programs and how to program the device. Now we've removed the packaging, we can get a closer look at the FX system and the FX microcomputer. So underneath this transparent cover here, we have access to the green electronic blocks and the red translucent computer unit itself. These green translucent blocks contain electronic components. So for example, here we have a 10 microfarad capacitor, and you can see it inside the block there and hopefully through the sides as well. And it's just been soldered to the terminals following the diagram and illustration on the top of the block. These terminals allow us to easily press fit components together in this pegboard. Now, some blocks are just wire links, and so as an example, this is a wire link block, and as you can see, this just has a wire soldered to the two terminals, and where terminals aren't required, they aren't provided on the block. Now, this particular layout of blocks is as illustrated on the cover of the box, and it provides two important functions in this particular configuration. The first is it provides electronic power to the FX computer unit, provides electricity through these terminals on the sides, and these two connections here provide connections to the volume control and through to the speaker so that the system can make sounds. I've already gone ahead and put in the 6 AA batteries required for this unit, and this unit runs at 9 volts, as illustrated by this 9-volt bulb here. Now, if I turn it around, you can see more clearly that that is indeed a 9-volt bulb, but the correct orientation for this circuit is upside down. Now, if you've got an EX system or if you used an EX system kit, you might know they have 4 AA batteries in, so they run at 6 volts, and therefore you shouldn't use the bulbs from those kits in this kit, as they might be damaged by the higher voltage. Now, I'm going to go ahead and turn this on here, and you'll hear there's quite a loud whine. Now, you can adjust that with the volume control here, and you can see that as you go through the volume, it fades in and out a little bit. But it's hard to get a good volume level with the unit at a reasonable amount of background whine. Now, I've seen a number of these units in Japanese and English on YouTube, and in fact in other European languages as well, and you'll see that they all seem to experience this whine, and I think it's an intrinsic problem with the unit, and I'll show you why I believe that. If I press 1 here, actually if I turn up the volume slightly, if I press 1 here, the volume of that particular whine goes down, but if I press 8, it goes much, much louder. So usually I'd want to run this at a little bit of a quieter volume so that I don't hear such a loud beep, but the problem is, as you can hear, there is significant whine, and I can barely hear the beeping. While I have the unit on, I want to show you that I can press down this switch here, and that illuminates that 9-volt bulb, and so that's the other function that this particular layout of blocks has. So I'm going to turn this off now for a moment, and I'm going to make one change that I usually do when I'm using the unit, and I take out this link block here, and I swap it with the 100K block here. And now this allows me to reduce the volume of the unit, and it also seems to get to a good harmonic resonance where the tone is not quite so obnoxious. So I'll use that for the rest of the video. And so I can turn the volume up now to the point where the whining is probably at its quietest, and the beeping is not obnoxious either. So this is usually how I would use these units. So I'm going to go ahead and turn this back off again so as not to damage it, but I want to show you the computer unit itself. We can take it out, and on the underside of this we can actually see the computer unit. It's resistors that are provided for the LEDs. We have the main processor unit here, some capacitors, and a ceramic oscillator here, ceramic clock for the computer that runs it at 400 kilohertz. Now, I have actually got 2 of these units, so I haven't taken this one apart, but I have taken my other unit apart, and that allowed me to take some nice photographs of the inside. And so I have the pictures from the inside here of my other unit, And you can see this is the front of the circuit board, which is represented by this block here. And you can see the display and the LEDs that are available on it. Now this bodge wire inside is original. It's not something I added. There was no damage made to my unit in particular. So that is an original bodge wire in the design. These are the contacts for the keys. And if I show you the next page, I have gone ahead and edited that to show where all the key layouts are and show the hidden traces that were underneath various components. So you can more clearly see what those would have looked like. I also went ahead and faded on a flip of the circuit side of the board, and so you can see where each of the components are connected, and so you can see this has been mirrored, which is why the text on the chip is reversed. But this allows you to see the entire circuit diagram for the unit. Just for completeness, here is a photograph of the switch contacts, and they are just using some domes and an interstitial sheet, and this is the underside of those yellow buttons here that presses down on the domes to make the contacts on those original contacts we saw on that first sheet. So I'll provide a link to these photographs as well in the description. Now that chip that we saw in the unit here is what the computer is actually controlled by, and it's a Texas Instruments chip labeled MP1312. This particular one is dated 82/27, so week 27 of 1982, which is around, predates the October time period on the box on my one. So again, dating this whole unit to 1982. Now that Texas Instruments chip, we actually do know what it is from the Japanese article I mentioned to you earlier. And so you can see here, it's labeled as a TMS1100 chip. And this is sort of the baby brother of the TMS1600 that's used in the Microtronic, which you can see in a previous one of my videos. Now, that's not to say that the computer is programmed with the TMS1000 instruction set. In fact, it's not. It has its own custom instruction set, just like the Microtronic computer does. And so the instruction set that we're going to use is on that quick reference card that I showed you earlier. So what I've done is I've gone ahead and I've written a couple of programs for this computer. And the first one is called or commonly known as a Larson scanner. And so that just provides the LEDs blinking backwards and forwards across the display. So I'm going to quickly enter that program now, and then I will talk you through how that works. Okay, so I've entered that program, and I'm going to go ahead and run the program. And so to do that, we have to reset the unit. We press 1, which indicates the run mode we'd like to operate in, which is the normal run mode. And then we press run. And with any luck, we'll see the LEDs flip backwards and forwards across the display. You'll notice while the display is out, we don't hear that background hum whatsoever. Again, it seems to be the multiplexing of the display here, which is causing that hum on the circuit. But we are hearing a click sound as the LED passes through the third LED here, or the fourth LED, the one marked 3. And that's because that sound is created by that LED flashing. And so that the faster it flashes, the higher pitched the sound you get. So let's have a little look at that particular program. So you might have seen in the corner of the video, I was using this particular instruction sheet here to see how that was operating. So I'm just going to reset to stop that program. So this is one of the programming cards that we use to write our program. And so you can see here that this program is made up of 31 nibbles, a 4-bit value. So this is a 4-bit computer. And rather than try and look at this particular code here, I've gone ahead and I've written it in a slightly more easy to follow sheet here. And so this has provided some comments as well, rather than just the machine code and addresses. So you can see the first thing I do is set up the delay by transferring a 1 into the A register. I then specify the LED I'd like to start with, which is in this case the 1 LED, and you'll see why I don't start with the 0 LED here as we get through the program. I then choose to set R, which means set the R value, which is the R value is indicated by these LEDs. This is considered the R port on the unit. I then call the timer, which waits for approximately 0.2 seconds. So although I put A over 10 here as the comment, the time delay is actually the value in the A register plus 1 divided by 10. So it's a little bit more complicated than that. It provides the approximate time delay. And then we restore R again to the value in the Y register. and this turns off that LED as well. So we've turned it on, we waited a few seconds or a few fractions of a second, and we turned it off again. We then go ahead and increment the Y register to move to the next LED we'd like to illuminate, and we check to see if the LED is now set to 6, and that would be the last LED here. You see the one labelled 6. And if it's not set to 6, then we jump back to our increment part of the loop, and we go through this again, displaying the LED, incrementing the counter. Once we do get to 6, then instead of jumping back to increment, we instead switch to the decrement part of the program. And here, we still start by illuminating that LED, because we haven't illuminated the 6th LED yet. So we start by illuminating the LED. We call the timer as usual to delay the program execution. We then turn the LED off, and then we decrement the Y register. But we're actually using the add in Y, so adding into the Y register the value F. Now, because this is a 4-bit computer, if we add F to it, the overflow means that we end up essentially subtracting 1, because the overflow value in the remaining bit essentially gets discarded. Or it would do, but as we can see from our programming reference sheet here, when we add into Y, if there is a carry, the flag is set to 1. Now the flag is important because that tells us whether or not we should use the following jump instruction should execute. So if there's been an overflow, so if we have a value in that register greater than 0, then that will overflow, the flag will be set, and we will jump back to decrement because we need to decrement again. So we need to keep decrementing until we get down to 0. When we get down to 0, we still go through this instruction because we will overflow to get to 0. But when we complete illuminating the LED, that means we now add F to that value and there is no overflow. So when there's no overflow, we find that our instruction here says that we don't set the flag is 0 here. And so that means that when we go to do the jump instruction, it goes, well, that isn't set currently. And instead it skips over that and goes to the next instruction, which jumps to the reset, which is up here, and sets us back to 1. So after we've done that 0th LED on the right-hand side, the next LED we need to illuminate is the first LED. And again, if I reset and run this program, you can see that's what happens, right? We get to the 0 and it jumps back to 1. Otherwise, it would try and illuminate the F LED, which would be over here and doesn't actually exist. Okay, so that's the first program, but I wanted to show you another program. So if you've recently watched my previous video about the Kenback 1, one of the programs in that particular video is the binary to decimal game that was in that particular computer. And I thought that was a really interesting program. Because it chooses to rewrite the instructions on the fly. Now, if we quickly look back again at the Larson scanner card sheet here, you see the program address space starts at 0 and it ends at 4F, and this is the space you're supposed to put commands in this computer. Now, this computer does allow you to access the memory and store stuff in memory, and when you go to do so, what it does is it goes ahead and it stores that in the memory address locations 50 to 5F, as detailed on this sheet here. And that is the address space immediately after the 4F here. Now, what's interesting about this particular computer is when you get to 4F, it will actually execute the next instruction from 50. So that means, although this is really more of a Harvard architecture, we can actually treat it slightly as a von Neumann architecture by moving some of our code into the memory access area. And we can use that same trick that John Blankenbaker used in his Kenback 1 to go ahead and rewrite the instruction to make a very efficient binary test game, as he did in his computer in the 70s. So I've gone ahead and I've got my program here. And so what we're going to do is, this time I'm actually going to show you me entering it in real time if you're interested in that. And I'll discuss through, at least for the first few, how that actually works. So let's put the program off to the side here. Okay. Now, I mentioned that I'm going to need to move that address space so that some of the code ends up in the 50 range. And so you can see what I've done here is I've printed out a different program sheet, and this time I've left the first column empty, so I can start my programming at 40 and continue all the way through to 50 as well. And in this case, it takes 32 4-bit nibbles. So how do we get and move around the address space of the computer? Well, we have an address set button here, and this allows us to specify where in memory we'd like to look at. And so if we press reset, it goes back to 0, 0, but we can actually go ahead and look at different memory locations. For example, we could go ahead and look at 50, and we type in 50, and we press address set, and now we can see what value is in address 50. Now, we know we're in address 50 because we have 5 in binary here and 0 here. And so remember, this is a 4-bit machine, and so we have two 4 bits for the address. We can go ahead and look at any particular space in memory. So we can go ahead and look at other locations. Let's say 20, address set, and so you went out at 2, 0, and there's an F in that location as well. But if we look earlier in the memory space, for example, 10, we can see there is a 4 in that particular location. Now that won't match this program yet because we're about to enter that in just a second, but it will match the program from the Larson scanner. And in fact, I can verify that by just looking at this sheet here. And we can see address space 10 contains a 4. We can go and verify any of those that we're particularly interested in. For example, let's go and see what's in 0A. So I can type 0A, address set, and we should see a B there, and we do, which is the AIY instruction. And of course, we can verify that by looking at the quick reference card and say if we see a B, that is indeed an AIY instruction, add into Y. Now we know how to move around the address space, let's think about how we can enter data into the machine. Well, we want to start at address 40 in this case. So I'm going to reset here, and I'm going to type in 40 and address set, and we can see there's currently an F in that location. Now this particular type of memory in this chip tends to default to F, but it's not guaranteed. It could be entirely random, but it is commonly F when you power it on for the first time. Now, in this particular location, we need to put in the TIY instruction. And again, we can look at our quick reference card to see what is TIY, and we can see that's an A, and you can see I've already hand assembled this into the machine code column here. So we're at address 40, we can see here for 0. We want to put our A value in, we press A, and then we can press increment. Now that saves that in the memory location and moves us to the next memory location. Okay, so I can go ahead now and actually just check that by typing in the address 40 and address set, and I can see the A that I entered, which is what is expected. Now, if I don't want to change the value in that location, I can just press increment and that won't change the value. And again, we can verify that by pressing 40 and address set again, and it's still an A, safe and sound. So let's go ahead, and we know we want A into address 40, we press increment, and then in the next location we want an E, and so we press E and increment, and then we want a 5 for an MA instruction, so we press 5 and increment, and then we want a 9 for an AIY instruction, so we find the 9 and press increment. Now again, all of these instructions, such as the AIY, or AIA in this case, sorry, is that maps to a 9, is available on the quick reference card, which is why I think this is super handy. Something that incidentally wasn't included with the Science Fair Microcomputer Trainer version. Okay, so we've got to address 44. We've just done 0 to 3, so we're now at 44, which is currently an F, but it needs to be a 9. And what I'm going to do is, just like before, I'm going to whiz through this in silence, and I'll speed up the video for you. Okay, so I finished entering the program now, and so I'm going to go ahead and press the reset button, and this actually resets us and brings us back to address 0, and that's why we can see the 8 here, which again is still the original program we have from our Larson scanner. So that's kind of neat. In fact, we actually have two programs in memory now. We have the Larson scanner program here in this particular memory location, and we have our binary to decimal game in these memory locations from 40 onwards and 50. Now, since we don't use the memory locations in the Larson scanner, we should be okay just to go ahead and still run the program by simply pressing reset 1 to set the run mode to normal running mode, and pressing 1, and our Larson scanner still operates as we expect. I'm going to reset here though, but I want to start my program at address 40. So what do I need to do here? Well, I need to actually set the program counter, and I do that the same way I do by inspecting any memory location, by doing 40 for the address and setting that address, and we can see we're now at 4 and 0. So now I want to run my program, my binary to decimal game, and that's easy enough to do. Again, I press 1 to set the run mode, and I press run. And so here it's showing me a particular a binary value that I need to decode into decimal or hexadecimal in this case. And this of course is 4 plus 1 or 5. And if I know it's 5, I can press 5 and I get a beep and I move on to the next one I need to enter. And this one here is 8 plus 4 plus 2, which is 14, which is actually the value E. Now I'm going to pretend I don't know that, and I'm going to say that's the value 9. So here I've programmed in that gives me a little error sound using the error sound built in, and it will keep showing me the same value until I get it right. So if I press 6 now, I still get my error value. So this is sort of a little bit extended on the original version from the Kenback 1, in that we now have some sound effects built in as well. As I said, I know this is the value E, so I'm going to press E, and then it moves on to the next one. And here we have 4 plus 2 plus 1, which of course is 7. And so I can go ahead and press 7 here. And then now we have no LEDs illuminated. I could be slightly confused here and think this is an F, but it's not. And you'll notice when I do that, the LED here in the middle illuminates. That's because it's flashing very rapidly, which is actually creating the sound effect. So I'll do that again. And you see that's creating the sound. And I can go ahead and impress the 0, which is the correct answer. And now I have 9 as the next one that's being displayed. 8 plus 1 for 9. Okay, so we could go through that and play this for as long as we like. And this is an infinite game, just as it is in the Kenback 1 version. In the original manual for that, they suggest that maybe you set yourself a timer of a minute and see how many you can get through. But actually, in this case, what I'm going to do here is I'm just going to go and explain how this program works a little bit more. And so, again, I've gone ahead and produced a slightly different sheet here that provides us some different details on how this program works. And so in this case, what we're doing and how we're managing to remap the memory at runtime, as I described, is we're starting off at address memory 40, and bear in mind we're starting at address memory 40, and we're setting the memory index, or the Y register, which is used to specify the memory index, to E, and that's specifying a particular memory location. And it will become clear what we need to use the E value in a minute. But we are then loading from that location using MA, so memory to A, and we can see that again on the quick reference card if you need to see that here. So it moves the location from the memory pointed to by the Y register into the A register. And at that point, we add 9 to it. And so this is one thing where I've done a little bit of a worse job than John Blankenbaker, in that I have not truly randomized. What happens here is every single value that you're going to be asked is just 9 later than the previous value you asked. It goes to a kind of effect of pseudo-randomization. It's kind of not immediately obvious that that's the pattern, and it gives you something to try and think about what the values are, especially when you're thinking about converting from binary to hexadecimal. Nonetheless, that's the way this particular version works. You could do a slightly more complex randomization, as is done in the Kenback 1, but that would be a little bit more involved and would require quite a lot more manipulation, as this is only a 4-bit machine, remember, so trying to extend out would require us to handle all that carrying into the next memory address space. Having said all that, we then go ahead and store that value that we've got, so the value we loaded plus 9, we store it back into the memory location E. Now, an interesting thing we then do next is we set the pointer to the memory location to 5, and we go ahead and store it in that location as well. And so we're storing it in 2 different memory locations. You can see from my sheet here, we're storing it in the location E. So we originally, when we start the program, we start with the C, we add 9 to it, which ended up giving us the overall value of 5, because this overflowed, and then the remaining value in the memory was 5, and that's why we saw the program start with 5, so that gets stored back into the location E. But then we've loaded the pointer to the location 5, or 55, and if we look at the 55 location, we can see there's a 0 value in there currently, but that gets overwritten by the same value we populated into E, which on our first run was indeed a 5. And so both of these locations have been updated to store a 5. The next thing we do is we jump to the DSP's position here. So there's a jump instruction that jumps to DSP, just here. So it's jumping over the error instruction. And the reason for that is that we only want to play the error instruction if someone's created an error. And actually, when we're going through at this point, when we've just updated the value, there's no error, right? We've just shown the new, we just want to show the new value to them as the thing to guess. And so now we call the display function, and there's a built-in routine for that. The display function just on here, And so if we look down the sheet here, we see it's an ED. And so the contents of M is displayed in binary on the binary LEDs. And it's a bit ambiguous here, but if you look in the detail of the manual that explains this in more depth, what happens is the computer goes ahead and displays the value in F on the first 4 LED, or the first 3 LEDs actually, and it displays the value in E, 5E, in the lower 4. And so that's why we've gone ahead and we wanted to populate this location here. Again, if we refer here, the location 5E, we want to populate that with the particular value we want the user to guess. So the F value is always O. We've set that as O, and so that means these LEDs don't get illuminated. But the final 4 LEDs here do get illuminated with the value that we've created for the user to correctly decode. Okay, at that point, then we go ahead and we call the KA instruction, and this means keyboard in, and it pulls the keyboard value into the A register. And what's interesting here is it says if no key is pressed, set the flag to 1. And this allows us to then loop around if no key was pressed by jumping back to the K in position, or the KA instruction. And so this will just loop through until someone presses a key. At that point, it does a compare in A. So it's comparing in the A register to a particular value. Now it says 0 here, but you see the annotation here, this is actually memory location 55. And we can see here is in our program card, we're comparing in A, and we're comparing the value in 55. And if you remember earlier in our program, we went ahead and we stored the value we want the user to guess, not just into the E location for display, but also into 55, and that's here. So the compare in A instruction would compare that to the value that we've gone ahead and set. So again, this is kind of like rewriting the instructions on the fly as done in the KenBack 1 version of this program. Now the compare in A instruction is detailed again on the card here, and it says that if it's not equal to the value, then the flag is 1. And so if it's not the value we're looking for, the flag is set to 1, and that means the following jump instruction will execute. And this jumps to the error instruction, and it goes here, and it goes to error, and it calls the error sound instruction, and that's why we get the error sound. We then immediately go ahead and redisplay on the display the value from the F and E values. Now the reason we need to do that is, as I mentioned, this middle LED is responsible for creating the sound, and when the sound is finished playing, the LED is turned off. Now that means it will have changed the value that's on this display. Now that may or may not be important depending on if this LED should be illuminated, but just in case, belt and braces, belt and suspenders as the Americans might say, we go ahead and we recall the display instruction to re-update the display with the same value that's still stored. And that means we can go through and check for another instruction. If they did get it right, so if it did match, the flag is set to 0, which means this instruction does not run. So the jump instruction here does not run. Instead, the call SHTS, or call short sound instruction, plays instead, and that's the positive confirmation that you get in the program. So I could have removed this. I could have also removed the error sound instruction as well, I suppose, to make the program simpler, but I thought they were nice additions because the program's already quite short. After playing that short sound, the confirmation that you've got it correct, it then jumps back to the next instruction, which is back at address 40. And the process repeats, where it again reads the value from 5E here and updates that by adding 9 to it. So I think this is a really nice little implementation that allows you to learn your binary to hexadecimal, rather than binary to decimal in this case, despite what I've put here, binary to hexadecimal. And it does so by just incrementing by 9 each time. But for the most part, I think that's a pretty nice way of doing it. And you can see that pattern now as the program's still running. If I go ahead and press 2, we can guess what the next value is going to be. And here we can see that is going to be exactly 9 forward. So 1, 2, 3, 4, 5, 6, 7, 8, 9, which brings us to B here. So 2 plus 9 is 11, 9, 10, 11, and that, of course, is correct. Now, of course, it does wrap round, so we can count 9 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, and we can see we're at 4, which hopefully we've already managed to guess, as there's only one LED illuminated, and it is directly under the 4. So I think that's probably enough about this particular computer system for now. If you've got a technique for shortening this program in any way, either this one or the Larson scanner, I'd be very impressed to see those. So I'd be very happy to see any programs you come up with. In fact, to make that easier for you to do so, I'm going to have a link in the video description to an online emulator for this and an online assembler that allows you to convert from the instruction set that we've seen in this instruction card to the mnemonics and also load those dynamically. I'll also include copy and pastable versions of these two programs I've shown in this video in the description that you can paste into that emulator as well. So I hope you found this video interesting, and I hope to see you in the next one.